Let us now solve this problem together. Elemental sulfur exhibits 5 common phases. There are 2 solid phases, and the 2 solid phases are known as S1 and S2. There is a liquid phase, which is known as S parenthesis L, and 2 gas phases. The first gas phase is S8 and the second one is S2. Here are the phases of sulfur at 1.0 atmospheric pressure. The specific heats and the latent heat of the transitions are also given. This is the first question. Identify the normal melting point and the normal boiling point of sulfur. The very first thing to note here is the word normal. The normal melting point and the normal boiling point will occur at 1 atmospheric pressure. So 1 atmosphere, that is the normal. And luckily for us, the data here was collected at 1 atmospheric pressure. Now, let us solve the problem. If we want to find the melting point, we will need to look for the data for sulfur when it transitions from the solid phase to the liquid phase. And if you look at this chart properly, you will see that that occurs right here, which means the melting point for sulfur, the normal melting point for sulfur, melting point is 388 Kelvin. Also, if we want to look at the temperature at which sulfur transitions from a liquid into a gas, we would have to look at this transition. And the temperature for that transition is 718 Kelvin. So the boiling point occurs at 718 Kelvin. Let us now solve the B part of the question. We want to calculate the total quantity of heat, which means we want to find Q, required to heat 1.00 gram of sulfur from a temperature of 25 degrees Celsius to a temperature of 150 degrees Celsius. Now, if you look at the table carefully, you would see that the temperatures are given in Kelvin. So, the first thing we are going to need to do is to convert the Celsius to Kelvin. If you add 273.15 to each of them, 25 degrees Celsius will become 298.15 Kelvin. 150 degrees Celsius will become 423.15 Kelvin. Let us now answer the question. To answer this question, the easiest way is to first draw a curve of the transition you want to study. So we're going to need a vertical axis and we're going to need a horizontal axis. The vertical axis, let us label it as temperature in Kelvin. The horizontal axis, let us label it as Q in joules. If you look at the table, below 368 Kelvin, sulfur only exists in the S1 form. So that means from a temperature of 0 Kelvin up to 368 Kelvin, sulfur only exists in the S1 form, and you can increase the temperature from 0 to 368 Kelvin by supplying energy to sulfur. And again, if you look at the table, if you now want to proceed from 368 Kelvin, sulfur will first transition from S1 form into the S2 form. At that point, we have a plateau. So this is S1 point. Now this is S2. Then you can now increase the temperature from 368 up to 388. So you can have an increase up to 388. And sulfur will transition from the S2 form into the liquid form at 388 Kelvin. So if you continue to supply energy, you will only get sulfur to transition from the S2 form into the liquid form. Now, do not forget, we only want to go as high as 423.15 Kelvin. But the next data on this table is that we can now heat sulfur so that its temperature would increase from 388, but we only want to stop at 423.15. So we will heat until we get to 423.15 Kelvin. We need to calculate the total amount of energy required to complete this curve. Let us now look at how we're going to accomplish that. Let us divide this curve into stages. Let us name this as stage A, from 0 Kelvin up to 368 Kelvin. Stage B will be when sulfur transitions from the S1 form into the S2 form. Stage C is when we increased the temperature of sulfur from S2 form into the S2 form, that is 388 Kelvin. Then we go to stage D, which is when sulfur transitions to a liquid. And then we have stage E, when we increase the temperature from 388 up to 423.15. Let us calculate the energy required for each stage, and then we add up all the values. But there is something very, very important to point out here from stage A. Stage A does not begin from 0 Kelvin. If you look at the question, stage A begins from 298.15 Kelvin. So we need to be mindful of that. This is where we actually begin, 298.15 Kelvin. That is where stage A begins. Then it terminates at the transition from S1 form of sulfur to the S2 form of sulfur. Let us now calculate the energy required for stage A. In stage A, the temperature is increasing from 298.15 Kelvin to 368 Kelvin, which means that Q for stage A will be equal to mc delta T. Let us plug in the values. The mass is 1.00 gram. The specific heat capacity for sulfur in stage A is given as 0.73 joules per grams per Kelvin. And the change in temperature is from 298.15 to 368. Final minus initial. If you cross out the units, grams will cancel out grams, Kelvin will cancel out Kelvin. It is always very important to follow the units. So for stage A, if you put in all of these values into your calculator, you will get 51.1 joules. For stage B, in stage B, the temperature is not changing, which means that Q will be equal to M multiplied by the enthalpy change to go from S1 form of sulfur to the S2 form of sulfur. And if you plug in the values, that will be 1.00 gram for the mass multiplied by the delta H given is 0.401 kilojoules. We need to change the kilojoules to joules. So that will be multiplied by 10 to the power 3, since kilo literally means 10 to the power 3 joules per mole. But there is a little problem here. If you look at the two units, the unit for mass is in grams, while the unit for the latent heat is joules per mole. We will need to change the mole to mass. And since we're dealing with sulfur in the monoatomic stage, to change the mole to grams will be 1 mole of sulfur. From the periodic table, that should be 32.06 grams. And if you cancel out the units, moles will cancel out moles, grams will cancel out grams, which leaves you with only joules. And if you put this into your calculator, you should get 12.5 joules. Let us now move on to stage C. In stage C, the temperature of the S2 form of sulfur is increasing from 368 Kelvin to 388 Kelvin, which means Q equals to mc delta T. And if we plug in the values, the mass is 1.00 grams. The specific heat capacity for sulfur in stage 2 is 0.78 joules per grams per Kelvin. And the temperature change is 388 Kelvin minus 368 Kelvin. Again, grams will cancel out grams, Kelvin will cancel out Kelvin. If you put all of this into your calculator, you will find out that stage C should give you a value of 15.6 joules. Let us now proceed to stage D. In stage D, as can be seen from the curve, the temperature is not changing. However, sulfur is transitioning from the solid state into the liquid state. So Q will be equal to mass multiplied by latent heat of fusion, which is another way of saying that melting is occurring. If you plug in the numbers, 1.00 gram is the mass. The latent heat of fusion is 1.722 kilojoules. That will be times 10 to the power 3 joules per mole. That was what was provided. However, we know that we need to change the mole to mass. And for sulfur, 1 mole of sulfur has a mass of 32.06 grams. Grams will cancel out, moles will cancel out. And if you put all of these numbers into your calculator, you should get 53.7 joules for stage D. And then we go to stage E. In stage E, the temperature is changing from 388 Kelvin to 423.15 Kelvin, which means that Q is equal to mc delta T. Plug in the numbers. Mass is 1.00 gram. The specific heat capacity of sulfur around that temperature change is 1.04 joules per gram per Kelvin, and the temperature change is 423.15 Kelvin minus 388 Kelvin. Grams will cancel out grams, Kelvin will cancel out Kelvin. If you put all of this into your calculator, you should get 36.4 joules. Now let us answer the question. The total heat required will be equal to the heat required for stage A plus the heat required for stage B plus the heat required for stage C plus the heat required for stage D plus the heat required for stage E. And if you add up all of those together, you should get 169.3 joules.